Hi everyone, welcome. Today we are going to see in this video the definition of linear transformation examples, what is the negative of a linear transformation, what is zero transformation and identity operator. These are the things we are going to see. Is it? Okay. Now see. Linear transformation. In order to say that define the linear transformation, the other name for linear transformation is vector space homomorphism. It is also called as vector homomorphism. Vector homomorphism or linear transformation, both are same. Now, in order to define a vector space homomorphism, you need two vector spaces. Let U and V be the two vector spaces, but these two vector spaces should be defined over the same field F. Okay. Now, if F is a mapping from U to V such that it should satisfy two properties, they are f of alpha plus beta is equal to f of alpha plus f of beta. For every alpha beta belongs to U, f of a alpha is equal to a into f of alpha for every a belongs to f and alpha belongs to U. If these two properties are satisfied by any mapping from U to V, then that mapping is said to be a vector space homomorphism or linear transformation. See here. What is U? U is a vector space. This is let U plus dot is a vector space and V is another vector space, let it be V plus dot. These two vector spaces are defined over the same field F, let it be the field F. These two vector spaces are defined over the same field F. What is F? Small f is a mapping, or you can take T also you can take. F is a mapping from U to V. Let alpha and beta are in V. Since f is a mapping, where is f of alpha? F of alpha and f of beta are in V. Is it? Now, alpha beta are in V. U is a vector space. Therefore, can I say that alpha plus beta is in U? Alpha plus beta is in U. Since f is a mapping, where is f of alpha plus beta? In U. In V, sorry. F of alpha plus beta is in V. Alpha plus beta is in U. Now, what is F? You have taken F as a field of scalars. A belongs to F. Where is A? A is in F. Now, A dot into alpha will be in U with respect to this scalar multiplication. Okay, because U is a vector space, it is closed with respect to scalar multiplication. Here, F of alpha is in V, A is on F. So, A dot into F of alpha will also be in V. See here. Now, this dot is different from this dot. This dot is the scalar multiplication of U. This dot is the scalar multiplication of V. Okay. Now, if you consider f of alpha plus beta, this will be equal to f of alpha plus f of beta. Okay. If it happens, now this is the first property of the homomorphism, vector space homomorphism. What is the second property? F of a alpha should be equal to a into f of alpha. Is it? Now, if these two properties are satisfied by the mapping F, which is defined from U to V, then that mapping is said to be vector space homomorphism or linear transformation from U to V. F is a linear transformation. See here. Now, this plus is different from this plus. Why? This plus is the vector addition of U. This plus is the vector addition of V. Similarly, A dot alpha, the dot in between A and alpha is different from the dot in between A and f of alpha. This dot is the scalar multiplication of U and this dot is the scalar multiplication of V. Okay. Now, if these two properties are satisfied by any function f, which is defined from U to V, then we will say that it is a vector space homomorphism or linear transformation. Is it clear? Now see the definition. Now here, see, the mapping f from U to V is called homomorphism if f of alpha plus beta is equal to f of alpha plus f of beta, f of a alpha is equal to a into f of alpha. Is it? Now you are saying this is vector space homomorphism. If f is only onto, then you will say that it is vector space homomorphism, and if it is 1 1 and onto, you will say that it is a isomorphism. Now see, combining these two properties in more general way, we are bringing the definition of linear transformation. What is a linear transformation? This usually linear transformation T is defined, it is denoted by T. Usually the linear transformation is denoted by T, and T is a mapping from U to UF to VF such that T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. That is nothing but you combined these two properties and you had put the definition of linear transformation in more general form. What is the definition of linear transformation? If T is a mapping from the vector space U to V, when U and V are defined over the same field, if T satisfy the property T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta, then T is said to be linear transformation. Is it okay? Now, there is no difference between this definition and this definition. Both are same, but it is in general form, more general form you put it. Okay. Now, this linear transformation is said to be linear operator if T is defined over the same vector space. That is, T is a mapping from UF to UF. T is a mapping from UF to UF such that T of A alpha plus B beta is equal to A into T of alpha plus B into T of beta. Okay. If it is like this, we will say that T is a linear operator. Instead of U, if you take T is from UF to F. What is F? F is the field of scalars. Then you will say that this is linear functional. Linear functional. This also should satisfy T into A alpha plus B beta is equal to A into T of alpha plus B into T of beta. B into T of beta. If it is satisfied by this mapping, then that mapping is said to be linear functional. What is linear operator? When the transformation is defined on the same vector space, then the linear transformation is said to be linear operator. If the transformation is defined from the vector space to the field on which the vector space is defined, then it is said to be linear functional. Okay. Now see what is the next one. See the example. Now the mapping T from V3R to V2R defined by T of xyz is equal to x minus y, x minus z, show that T is a linear transformation. Now what is T? T is a vector space from V3 of R to V2 of R. So let alpha and beta, take two elements in V3. Alpha is x1, y1, z1, beta is x2, y2, z2. They both belongs to V3. Let AB belongs to R. Consider T of A alpha plus B beta. You have considered T of A alpha plus B beta. What you have to prove? A into T of alpha plus B into T of beta. That you have to prove. In order to prove that, T of A x1, y1, z1 plus B into x2, y2, z2. Now by scalar multiplication and vector addition, if you add ax1 plus bx2, ay1 plus by2, az1 plus bz2, this is like, in place of x you are having ax1 plus bx2, in place of y you are having ay1 plus by2, in place of z you are having az1 plus bz2. Apply the given transformation. T of xyz is defined as x minus y and x minus z. X is the first component. Here ax1 plus bx2 and second component is ay1 plus by2, ax1 plus bx2 minus ay1 minus by2, comma ax1 plus bx2 minus az1 minus bz2. Now if you arrange these terms, now take here ax1 minus ay1, a into x1 minus y1. From here a into x1 minus z1, that is the second component. Similarly b into x2 minus y2, x2 minus z2. Now this is nothing but t of x1 y1 z1 from this transformation, and this is nothing but t of x2 y2 z2. So a into t of alpha plus b into t of beta. If T is a mapping from V3 to V2, T of xyz is defined as x minus y, x minus z, then you are able to say that T into A alpha plus B beta, for any alpha beta belongs to V3, AB belongs to R, you are able to show that A into T of alpha plus B into T of beta. Therefore, by definition of linear transformation, the given T is a linear transformation. Is it okay? Now see the next example. Next example. The mapping T from V3 to V1 defined by T of ABC is equal to A square plus B square plus C square. Can T be a linear transformation? That means you have to verify whether T is a linear transformation or not. Now see here. What is T? T is from V3 of R to V1 of R. Let alpha is equal to x1 y1 z1, beta is equal to x2 y2 z2. Those three are the elements in V3 of R, and P comma Q belongs to R. Consider T of P alpha plus Q beta. Now P alpha means P into x1 y1 z1 plus Q into beta means x2 y2 z2. Now if you scalar multiply, this will be P of x1, P of y1, P of z1, Q of x2, Q of y2, Q z2. Now if you add Px1 plus Qx2, Py1 plus Qy2, Pz1 plus Qz2. Now you got. Now in place of A, B, C, if you compare this with this transformation, in place of A you are having Px1 plus Qs2, in place of B you are having Py1 plus Qy2, in place of C you are having Pz1 plus Qz2. What is T of ABC given to you? A square plus B square plus C square. So here also it will be Px1 plus Qx2 whole square, Py1 plus Qy2 whole square, Pz1 plus Qz2 whole square. Is it? T of ABC is that. Now again consider P into T of alpha plus Q into T of beta. Keep it as 1, and now you are considering P into T of alpha plus Q into T of beta. P into T of x1 y1 z1 plus Q into T of x2 y2 z2. That is, T of x1 y1 z1 is x1 square plus y1 square plus z1 square according to this operator. Therefore, P into x1 square plus y1 square plus z square plus Q into x2 square plus y2 square plus z square. This is P x1 square, P y1 square plus P z square plus Q x2 square plus Q y2 square plus Q z2 square. Now let it be 2. From 1 and 2, you can say that T of P alpha Q beta is not equal to P into T of alpha plus Q beta, because here even though you get P square x1 square, Q square x2 square, like that the terms, these two are not equal. Therefore, you will say that T is not a linear transformation. Okay. Now See the next example. It is from T. Here show that the transformation T from R3 to R3 is defined by T of xyz is equal to x minus y, 0, y plus z is a linear transformation. See here, in